All right, so in this video, we're going to be looking at how to evaluate limits numerically using Excel. So I'm going to look at these two examples. I picked them for their relative simplicity, but also because they illustrate the points that we're going to be trying to make. Now, the way that I usually set these up is I begin by starting with a range of powers of 10 that I want to implement. And so based on the distance from the original point that I'm actually trying to evaluate the limit at, I go a distance of 1 unit away maximum, and then I get closer and closer and closer by a power of 10. So one thing to kind of keep in mind as you're doing these is you don't want to get too many decimal places in. You don't want to go to, like, say, 10 to the minus 11th, because what will tend to happen is you'll run up in some cases against the ability of the computer to represent numbers accurately, and you'll start to see deviations from your idea of convergence. So these are the numbers that I want to use to evaluate, and I'm going to we'll call this n, and then we'll call this the step size. And the step size is basically just going to be 10 to the power of my number for everything except my C value. Actually, it's going to be 10 to the negative power. If you're going to infinity, you want to use the positive power. If you're going to closer and closer, you want these to be getting smaller, not bigger. So our maximum distance away is going to be a 1. Step size here is basically 0 because we are on the point that we're trying to evaluate. Now, for both of these, we're going to be evaluating them at a position where the function is going to be undefined. And we're going to see that division by 0 error when we actually evaluate the limit. Right now, we're just setting up the x values that we want to plug into that value. Now, the value that we're going to use to evaluate is now going to be based on our C value. So I'm going to do the second one first, since it's just a polynomial. I'm going to use 3. And then each one of these values is going to be this value right here. And I'm going to put dollar signs on it so that when I copy it, it doesn't move. On the positive side, above the value, where I'm coming in from positive values or values that are larger than it, I'm going to do plus my step size. And now I can copy this down. And then on the other side, I'm going to do my C value. But now I'm going to do minus my step size. Now, for some of these, as the numbers get very close, you're going to see that they're not going to show all the decimals. You can force it to display more decimals. That's my C value. There we go. So again, you can either widen the columns or do what you need to in order to have it display more values so that you can actually see that it's converging to 3 from both sides. Now, the way that I find that this is typically going to work better in terms of setting it up is I'm going to solve for or evaluate the numerator and the denominator separately. Now, the way that this helps me is that I can verify that the top and the bottom is going to both result in 0. So I'm going to get division by 0 for both of my examples. And that's when the numerical limit should be applied. You don't need to apply it if a function is defined, or if you're not doing 0 divided by 0. If you're doing some other number divided by 0, it's not going to, you're not going to get a limit. But it also means that I don't have to do lots of extra parentheses in order to get it all into a single expression. So my top function, again, I'm looking at this one, is going to be this value squared minus 2 times this value minus 3. And the bottom is going to be this value squared minus 7 times this value plus 12. It just so happens to be 0 there. Don't worry about it. And then, because we're not interested in what's going on at 4, the top divided by the bottom. Again, I got division by 0 here, but for this particular problem, that's fine. And then I'm going to copy this all the way down. Now, okay, one thing, don't worry about these values for a second. One thing you want to keep in mind, at C, at the point, we have 0 divided by 0. You should expect this to happen. That is your confirmation that this is an appropriate solution process for you. Then you can look at how these values converge on either side of your value of your interval. So as we get closer and closer to our value x equals 3, what is our function approaching? Well, on this side, it seems like it's getting to -4. And on this side, it also seems like it's getting closer and closer to -4. Again, you can display more decimal places if you really want to. Widen your columns if you get those weird things. And it will display, again, more and more and more decimals. And you can see you are, in fact, getting closer and closer and closer from both sides to -4. So that is our first example. We can repeat the second example basically the same way. In fact, I'm just going to copy this. And I'm just going to change a couple of things. So in my second example, I want to go to 4. And I want my function to be a little bit different. So my function is going to be this value minus 4. And this one is going to be the square root of this value minus 2. And the other thing that I need to change, of course, is my reference. I don't want to refer to this value anymore. I want to refer to this value. So that is J10, not C10. And then I want to copy these. All right, so again, let's confirm. We have division by 0 at 4. These are all pointing at the correct values. Okay, great. This number could be a little wider. There we go. Something didn't copy. There we go. Again, you want to make sure you're getting closer to 4. So your limit here is your values are getting closer and closer to 4. We want these to be negative, not positive. There we go, and that's better. And again, we can see that this does appear to be getting closer to 4. We can widen our columns to verify that, yeah, the decimal places are there and they are getting closer to 4 from the other side. These, in this case, one goes to -4, one goes to +4. That's accidental. But these are things that you can confirm algebraically. If you were to evaluate these two functions, there are algebraic ways to simplify expressions like this so that you can evaluate them exactly. But there's certainly going to be other problems where that is not the case. So e to the x minus 1 all over x is not going to be something that you can evaluate just by simplifying algebraically. You either need calculus or you need to do it numerically. For that kind of an example, you're going to get a weird answer, which will be e. And so it'll be a little bit more difficult. It's not going to be an integer to verify that that is in fact your answer, but it will be something that you can do. Sine x over x, for example, that will be an integer value, but that is also not one that you can evaluate by using other algebraic techniques, but you can do it numerically like this. And again, the nice thing about this method of doing this is that once you set up your first example, as you saw, it was relatively easy to make adjustments and set this up for another example, another function. You don't have to reinvent the wheel from scratch every single time. So you can essentially build yourself a kind of numerical limit calculator.